Thanks for the invitation and giving me an opportunity to speak. So today I'm going to talk about something about large charge and holography. So the theme of the talk is basically like large charge and holography for superconformal field theory. And especially like the kind of questions that I want to address are for example, what's the counterpart of the large charge effective field theory in holography? And what we can learn from large charge about holography, or what we can learn from holography about large charge. So, and before I start, let me just make one disclaimer. So for concreteness, I will focus on n equals 4 super mills in 4 dimensions, and all the explicit results are for n equals 4 super mills. I believe many of the results and argument would generalize to other n equals 2 superconformal field theories, but the details need to be worked out. Okay, so this is a plan of the talk. So the talk is going to consist of 3 parts. And the first part is some relation, like basic comments and general comments about large charge and holography. And it's based on mostly unpublished stuff and partly based on some discussions with Clay Cordova and Frank Coronado. Frank is a postdoc in McGill, and Clay, I think many of you know, who is in Chicago. And in the second part, I'm going to say something about double scaling limit and the central extension of the symmetry, which is based on the work in progress with Joel Caetano in Simon Center and Ethan Wan in Harvard. And the last part is about correlation functions of D-brane, which is based on the paper that we put out this March with Pei-Hei Yan and Junbao Wu. Both are in China from Tianjin University, and Yunfen Zhan, who is in CERN. Okay, so let's start. So the first topic is about large charge in holography. So let me first make a general remark. So as we know, well, probably many of you know that the ADS-CFT relates some operator living on the CFT side with some like a excitation or particle states in ADS. And so this is a kind of like a cartoonish picture in which you insert the operator at the boundary of ADS, and that is going to emit some particle or excitations in the bulk of ADS spacetime. And to be concrete, let's discuss n equals 4 super Mills theory with U and gauge group, and that is going to be due to quantum gravity or string theory in ADS 5 times this 5 spacetime. And the important point is that in the holography, depending on the size of the dimension of the operator, the dual excitations are different. For example, if you consider the operator with dimension of order 1, and they are going to be due to graviton or light matter fields. And whereas if you consider operator with dimension of order n, where n is the rank of the gauge group, they are going to be due to D-branes. And finally, if you consider operator with dimension of order n squared, they are heavy enough to deform the geometry. So on this side, you no longer have ADS 5 times 5 spacetime, but you get some deformed geometry. And sometimes this deformed geometry has horizon, and this is probably what normally people have in mind, for example, in the context of like a relation between heavy operators and black holes. But in some cases, you can also get some operators without horizons. And in one example, in the context of n equals 4 super Mills and ADS 5 times 5 spacetime, are called Lin-Looney-Maldacena geometry, which are due to half BPS operators. And the simple way to get the operators with large conformal dimension is to take other quantum numbers to be large, for example, spin or U1 charge J. And the reason why this is useful is because of some BPS bounds or unitarity condition of CFT. If you take other quantum numbers to be large, then automatically the dimension of the operator also becomes large. And of course, this is the large charge seminar. So today I'm going to focus on the operator with a large U1 charge J. Okay. So let me just briefly review the very, very basic about large charge expansion. Of course, I don't think I need to review this for this audience, but just to make sure we are on the same page. Okay, so one of the fundamental or most basic result for the large charge analysis of conformal field theory, especially in generic conformal field theory, is this semi-universal prediction of CFT data at large charge. And in particular, the most basic one is this one. So it basically says that if you consider a CFT with U1 charge, U1 symmetry, and then consider operator with large J, large quantum number, the dimension of the operator, the minimal dimension of the operator with U1 charge J, scale like this, J to D over D minus 1 for D-dimensional CFT. And as you know, it's very easy to derive this formula. And this is basically coming from the scaling argument. So in order to do this, we need to consider CFT on RT times SD minus 1. So you do the radial quantization, and in particular, take the radius of SD minus 1 to be R. Then the energy of the state, which is dual to which corresponds to this operator insertion, is given by delta minus R, which is just the dimensional analysis, whereas the charge is given by J. And now, if we further assume that the large charge state in the R infinity limit becomes a state on a flat space with finite density and finite energy and charge density, then in terms of energy and charge density, we should get this formula. So energy should scale like R to D minus 1, and the charge should also scale like R D minus 1, because R D minus 1 is the space volume. And combining these two relations, then we can immediately see that delta should scale like R to D because of this additional R, and that is going to be given by J to D over D minus 1. But I should also say that this scaling doesn't really involve the writing down the large charge effective field theory, and it doesn't really rely on a particular large charge effective field theory. And in fact, you can also get the same scaling by analyzing ADS RN black hole in the limit where J is much larger than CT. And this was discussed in this nice paper. But of course, we can do better than this leading prediction, and that's basically the key point of the large charge expansion. And so the idea of getting 1 over J correction is to write down the effective field theory. And in particular, in 3D, if you assume that you have one scalar degrees of freedom in this large charge limit, then you can basically systematically analyze the large charge EFT. And that basically gives you a prediction about the correction. And in particular, you can make some universal prediction about this constant term. And furthermore, EFT approach also predicts delta for excited state and OP coefficients. And in addition, under certain assumptions, you can rederive these results from the bootstrap. Okay, so however, as I wrote in the previous slide, this is a semi-universal prediction. And the reason why I wrote semi-universal is basically because this is, for example, in particular, not correct for superconformal field theory. And this is kind of obvious because I was saying that the minimal conformal dimension of the operator with charge J should scale like this. But obviously, this is incorrect for superconformal field theory because of the BPS states or BPS operator, for which the delta is linear in J. And the basic reason why this scaling fails is very simple. So if you consider BPS state and then take a large R limit, then this should go to a state on a flat space with zero energy but finite charge density. And the reason why so normally, if you just consider generic state and then a generic field theory, and if you want to create a state with finite charge density, then you need to put some matter on top of the vacuum, and that is going to create also energy density. But in the case of supersymmetric theory, because supersymmetric theories have flat direction, or in other words, vacuum manifolds, you can basically construct a state for which energy is 0, but J is non-zero. And one way to construct such a state is to take some like a state on the vacuum manifold, let's say parameterized by theta, where theta basically specifies the direction to which the direction of the vacuum expectation value of the complex scalar field. And then you multiply this factor and then integrate over d theta. And if you construct such a state, then you can see that like this state has charge J, or where although like this state has energy 0. Of course, like considering such a state is not allowed on a flat space because like we are considering like a superposition of the super selection sectors. But because we are just, well, strictly speaking, we are not really on a flat space because we are on a sphere. It's kind of allowed to have a state which is approximately given by this expression. Okay, so, and for rank 1, n equals to superconformal field theory in 4 dimensions, and which have the 1-dimensional vacuum manifold, this idea of like relating the BPS states to the vacuum manifold was made very, very explicit. In particular, in this paper, and they show that you can actually perform the large charge expansion based on the Coulomb branch effective field theory. The relation between the two is kind of already suggested in this expression, because this large charge state is given by some superposition of the state on the Coulomb branch. Okay, and in particular, you can predict this behavior of the 2-point function of like a chiral and antichiral operators in the large J limit, and that is in agreement with the localization. Okay, so far so good. But you might ask, like, what happens if you consider higher rank, a theory with higher rank, not just rank 1. So by rank 1, for example, in the context of n equals 4 supermers, I have in mind something like SU2 n equals 4 supermers. So for higher rank, I should say, I guess not much has been studied. And the reason is because there are like several difficulties. And the first difficulty is that, for example, if you consider n equals 4 supermers with SU-n gauge group, then first of all, the vacuum manifold is multi-complex dimensional. And depending on where you are, there is actually a variety of Hickson patterns. So in the case of SU2 gauge group, if you give a VEF to some scalar field, you are automatically in a regime where effective low energy effective field theory is given by the U1 degrees of freedom. But if you are in a SUN theory, then depending on where you are, the low energy might be given by U1 times SUN minus 1 or U1 to n minus 1. So of course, like when we normally talk about Coulomb branch effective field theory, we normally have in mind this Hickson pattern, but in principle, there can be other Hickson patterns. And the second difficulty is the classification of higher derivative terms, but I have nothing intelligent to say about this. But this is, well, certainly a technical difficulty. And the third difficulty is the degeneracy of BPS operators. So in SU2 theory, there is basically only one chiral operator, chiral primary operator for each charge J. And this is because like this expression and this expression is identical in SU2 theory, where phi is some complex scalar field because of the trace relation. However, in SUN theory, these two are different. And of course, you can also write something in between. And so you can have like a multiple BPS operator with the same charge. And the last point is a little bit more technical. And I think it's only for people who actually worked on the subject. But the analysis of like, so if you want to get the results from localization, you cannot really take the like a localization matrix model, but you need to kind of like orthogonalize the operators that you get from the localization, because the localization results gives you the result for the correlation function on a sphere, but you need to translate that to the correlation function on a flat space. And this orthogonalization procedure, which is given by the Gram-Schmidt process, gets more complicated. And So I just wanted to make some remark about the point 1 and 3 in a toy model and see how and why these two difficulties are related. So that's what I'm going to talk about now. Any questions so far? Okay. So let's consider the simplest toy model, the complex matrix model, which is like a zero-dimensional field theory. So we have like a complex scalar, z and z bar, and I'm going to consider the two-point function of this complex of some operator, which is made out of, so always, I assume always made out of z, and O bar is made out of z bar. And I further assume that the action is given by Gaussian. So this is a complex matrix model, which is a little bit more complicated than Hermitian matrix model that people are familiar with, but you can still write the result in terms of eigenvalues. And using the result by Ginibre, this reduces to eigenvalues in this expression. And here I'm assuming that O only contains Z, so that's why like O is given by some function of Z, where O bar is given by some conjugate function. And let's for now take the simplest operator, which is a single trace operator, trace Z to J, and then try to insert this in this eigenvalue expression. So then, because we have this expression, and if you write it in terms of eigenvalue, this trace of Z to J gives you this factor, and whereas the complex conjugate gives you this factor.
Sorry, what
so
is
we
Z?
have like a two.
Sorry that I'm interrupting. What is ZJ?
ZJ, ZJ, sorry, here, Z to J, to the power J.
What is the lower index, ZJ?
Lower index, this one?
Yeah.
Oh, sorry, the J's runs from 1 to n. So like I'm having in mind some toy model for SU and Yang-Mills theory, let's say.
But the matrix Z is not diagonalizable.
Matrix is not diagonalizable, but like, well, I mean, okay, so so it's not diagonalizable, but you can like make it triangular, like upper triangular in this particular action, for this particular action of the Gaussian.
So what, so the Z, this runs over the entries on the diagonal?
Yeah, entries of the diagonal, yeah. So you can make Z upper triangular and Z bar lower triangular, if I remember correctly. And then like integrate out other parts. And this kind of simple expression doesn't work if, for example, insertion of operator contains both Z and Z bar. And it's important that like a Z is kind of holomorphic in Z. So always holomorphic in Z. Okay. So, right. So thanks for the question. And so we have like a two summation over two indices, K and L. So, okay, so it's true that like, so maybe I wrote this eigenvalue is not right. So it's more like a diagonal element. So we have like a summation over two indices, but if you look at other parts, then you see that other parts are invariant under the U1 rotation, which rotates Z in one direction and Z bar in the other direction. And because of that, the non-zero contribution basically comes from K equals L. So that reduces the summation to one summation over K. And that gives you this expression. And furthermore, by using the permutation invariance, because the other parts are completely invariant under the permutation of K's, Z1 to Zn, you can further reduce this to this expression, where you get like a Z1 to 2J. And if you look at this expression, it's clear that this basically gives you a source term only for Z1. So it treats Z1 differently from all the other Z's. So this basically suggests that, so if you just consider the single trace operator and then take a large charge limit, the relevant physics is given by the Higgsing pattern where UN is broken down to U1 times UN minus 1. You can, okay, so, and then let's next consider the next simplest one, which is the double trace operator. which is like a trace Z to J1 and trace Z to J2. And by going through the same analysis, now we have like a summation over 2 indices because it's a double trace operator. So you might think that this corresponds to U1 square times UN minus 2 Higgsing pattern. But this is precisely speaking not correct because this summation over N and M consists of 2 parts. The first part is given by like N not equal to M. And the second part is given by N equals M. And this first part corresponds to the symmetry breaking pattern UN going to U1 squared times UN minus 2, whereas the second part is given by U1 times UN minus 1. So this also shows that if you consider this double trace operator, this doesn't correspond to like a definite Higgsing pattern. So it corresponds to a mixture of Higgsing patterns. So in order to really like extract this Higgsing pattern, you actually need to subtract this. So in other words, if you just consider double trace operator, then like so this suggests that it's very hard to describe it using the effective field theory because that contains like 2 different EFT-like regime. So this analysis can be generalized to other Higgsing pattern, and also like although I use some very, very simple complex matrix model, this can be made a bit more rigorous for N equals 4 super-M-Mills because things can reduce to this kind of one-dimensional matrix model, matrix quantum mechanics, sorry. And a similar construction would work for N equals 2 superconform field theory, but again, this is just like a general remark and the details need to be worked out. But one thing I should emphasize is that like, so okay, you can keep doing this, but in general, writing down some linear combination gets rather complicated. And if you like increase the rank of the gauge group. However, in the large N limit, we actually know a good basis, which basically extract a given Higgsing pattern. And that's known as the Shota polynomial basis, and which is defined by this expression. So the Shota polynomial basis is labeled by a Young tableau, and it's given by sum over permutation. And here you have a character of the SJ permutation, and then you have like a product of J fields. These are assumed to be adjoint in the gauge group. And from various studies in the past, especially in N equals 4 super-M-Mills, we know what is the effect, physical effect of these Shota polynomial operator. So to summarize, like if you consider this, for example, Young tableau, which consists of 3 rows, roughly speaking, the length of each row corresponds to a magnitude of source term for the case eigenvalue. So this symmetry breaking pattern, so this Young tableau should correspond to this symmetry breaking pattern where you have U1 times U1 times U1 times UN minus 3. And in particular, if you just consider the single row Shota polynomial operator, and that is going to be given by, you can actually check it explicitly that in the leading large N limit, it's given by trace of Z to J, and that's consistent with what I just said. But I should also mention that there are also 1 over N suppressed terms. So this basis is a good basis in the large N limit, but it's probably not a good basis if you really want to analyze a finite N theory. Okay, so and another nice feature of this basis, and this is why I started talking about this basis, is they admit a very simple and nice holographic description. Okay, so what is the holographic description of these bases, these operators? So in N equals 4 super-M-Mills, this single row Shota polynomial is known to be dual to what's called dual giant graviton. which is the spherical D3 brane living on ADS5. So the world volume is in the global ADS is given by RT times S3, and which is contained inside ADS5. And the size of the D3 brane is given by J divided by N, which I denoted by small j. So as you increase the size of the charge of the operator, then this D3 brane gets bigger and bigger and approaches the ADS boundary. And if you have a multiple rows, then it just corresponds to like a multiple D3 brane with different size. Okay, so in the J equal infinity limit, as I said, the D brane approaches the ADS boundary, and it can be approximated by a flat D3 brane. Well, what I really mean by this is that here I drew a picture in the global ADS, but let's interpret this from the Poincare ADS slice. Then if you take J going to infinity limit, this spherical D3 brane approaches the boundary and can be approximated by the flat D3 brane. And this flat D3 brane is nothing but the holographic description of the n equals 4 supermills in the Coulomb branch, where the symmetry is broken down to U1 times UN minus 1. So this basically gives you a kind of geometric realization of the large charge expansion. So basically, this curvature expansion corresponds to the 1/j expansion. And the DBI action living on this brane should be interpreted as a large charge EFT. Okay.
Would this picture hold up to j of order n square?
I think in this particular operator, for this particular operator, I believe it actually holds. So this picture holds even for that operator. So this is a kind of like a very special operator. So normally, like if you have an operator with n squared dimension, then you might think that like you get some deformed geometry. But I think for this particular operator, you still get a D brane.
Okay.
Okay.
But
So this
it would be, you say a D brane, but I mean then it would be a whole big bunch of D branes though, wouldn't it?
Well, if you just like increase in this direction, then like the D brane just gets bigger and bigger.
Oh, I see, I understand. I understand. So making it order n squared really just means taking the D brane to be super horizon, super ADS
Right,
size,
right.
rather than sort of one ADS size.
Yeah, yeah.
Thank you, I understand.
And okay, so let me just also mention that, so this was the kind of holographic picture of what's happening. So let me just also give you some kind of like some understanding from the field theory side. So what's happening here, if you like have a very large J, is that like you are giving basically like a very large expectation value to like one of the entries of the scalar field, which is given by n times n. And if you give this expectation value, then this off-diagonal modes acquires a mass square, which is given by GML square times J. And in the large charge limit, we normally take a decoupling limit in which like these like massive modes decouple. So we want to take this to be very large. And so we want to take this combination to be very large. But if you combine this with the usual like Tfuftek limit, then the limit in which this becomes large is basically the same as limit in which this ratio becomes large. So that's why, so this is consistent with what I just said in the previous slide from the holographic point of view. So in this limit, you get something like a large charge limit, and that is going to be given by DBI action.
Can you give us at least a general understanding of what breaks when you consider the 1/n corrections? I mean,
okay, yeah,
just a picture, not equations, just
right. Yeah. I see 1/n correction. Yeah, that's a good. Yeah, so, okay. So for the one of, okay, so I think it's easier to understand from this picture, the holographic picture. So in this theory, so you have, and what I was saying is that like a theory living on the D-brane is like a large charge effective field theory. But in addition to that, we have like a bunch of closed string flying in the bulk. And if you include the one of n correction, then those closed strings start interacting with the degrees of freedom living on the D-brane. So this means that there are like you start seeing some light modes, which were not captured in the large charge EFT.
Okay.
And what are those light modes? And those light modes are basically these modes, because these are all lights. Although the interaction between this guy and this guy is mediated by the heavy guys, but there are still like a bunch of light guys.
Okay, thank you.
I have some question about this.
Mm-hmm.
So the DBI action. So if you're extremely naive and you just like take n equals 4 super Young mills and you go on this particular direction in the Coulomb brane, so you could write some effective action. So you would write a kinetic term for the U1, right? We will just write effective action for U1 vector multiplet. There isn't much you can do. So you just write a kinetic term. There is a 4 derivative term that's related to the anomaly. And then there is like an infinite series of terms.
Right.
On the other hand, the DBI action tells you that the answer is some square root. So it resolves infinitely many terms.
Right.
I've never understood, is this really correct? Like, is it supposed to be a true fact about the effective field theory of n equals 4 super Young mills?
Yeah. Actually, yeah, that's something I want to know. I'm curious to know, and I don't have an answer, but I actually have a slide next.
Well, one thing you can say is that the DBI action only resolves terms which don't have acceleration, only d phi, powers of d phi. So maybe the DBI action is some kind of expansion in acceleration, but
I see.
do with an expansion with large charge.
Right.
I never understood. There is some paper about it by Silverstein and Tong.
Oh, I see. Okay, I never looked at it indeed. Actually,
But they didn't clarify this issue.
I see. Yeah, well, what I wanted to say in this slide is much less elaborate. I mean, like it's just more like a much more crude idea. But Zoha was pointing out, like if I were to write down some kind of like a U1 EFT on the U1 degree of freedom, well, we can try to do it in the field theory, and then like there aren't so many terms, well, so many possibilities that you can do. But that problem is basically just identical to the problem that of like writing down like a large charge EFT for SU2 theory, because like if you only have a U1 degrees of freedom.
Right.
So this is a bit curious because like here, and in particular DBI action is supposed to describe the large N series, but like the problem of writing down the large charge EFT is identical to the problem of writing down large charge EFT for SU2 series. And I just wanted to make one comment that like a DBA action is of course like derived in the holography limit, but it has various nice features like a supersymmetry and also geometric realization of large charge expansion, and also it respects the S duality. So it might also capture, well, this is not logical argument, but it might also capture some aspects of SU2 n equals 4 subterminals.
But Shota,
yes,
this is something that is not that surprising because, say, when you look at ON and large N, that representation there, saying, you do get an action like just for U1, it's just that the couplings depend on N.
Right.
That's where the N is coming from, because you integrate out everything. It's like in your matrix, you're integrating out everything else. And then the effective action for the term on top depends on what you integrated out.
I see.
So I guess it's something similar.
I see. But DBI action, if you expand out square root, then like it predicts some particular patterns of the coefficient.
The DBI is different.
Yeah. I think the magic of the DBI action is that it seems to predict infinitely many terms.
Yeah.
And I actually honestly don't know if first this prediction is correct, and second, what is thrown away? What about these acceleration terms?
Okay, okay.
You mean the DBI action in ADS or in flat space?
No, the DBI action of a D3 brane, what Shota is talking about.
Yeah, I understand, but in ADS or in flat space?
In ADS.
I mean, I think even in Maldaceni's original paper, he actually said that the terms with just made out of first derivatives, just the velocity, non-acceleration terms. I think he said that the DBI action was uniquely fixed by the symmetries.
I actually wanted to say that Juan already discussed some aspect of this. Juan said that if you throw away acceleration terms in the ADS, this is unique. The square root is the unique answer.
Right. That's part's supposed to be true.
Now, I don't actually know. I mean, can you prove it at weak coupling? Because it's a well-defined statement about weak Hooft coupling. No, we can go to n equals 4 triangles, take weak Hooft coupling. Is it actually correct? I don't know.
I thought it was just a statement about the effective theory on the brane, on the single brane.
But it's a statement about the effective field theory for the vector multiplet of the U1. You can just do it at weak Hooft coupling.
Right.
So.
But I mean, at that level, I think it's just that you can't write down any other operators that obey those symmetries, right?
But Juan assumed a particular action of the conformal group on the degrees of freedom in the vector multiplet, and I've never figured out for myself if it's really correct in general, or it's just maybe an action that's true and strong at Hooft coupling. Nobody showed that this is correct at weak at Hooft coupling, as far as I know.
I have a more simple question. You said this operator corresponds to x in un to u1 times un minus 1. So you have in principle all the gauge degrees of freedom in the un minus 1, which are possibly strongly coupled. So these are 1 over n suppressed, or these are expected to be
the coupling to that degrees of freedom is 1 over n suppressed.
So that's what you were mentioning with the closed string.
Yeah, they are closed strings. So I'm going to, thanks a lot for the discussion. Yeah, this is indeed my intention of bringing this topic up. So lastly, I just wanted to mention that in the context of Coulomb branch effective actions, John Schwartz had a very speculative paper, which basically conjectures that a DBI action for the flat D3 brane also captures the low energy effective action of the Coulomb branch. But it's probably kind of interesting to revisit all these questions in the context of large charge expansion. Okay, so let me now move on to the next topic if there are no other questions. Okay, so now I'm gonna briefly discuss work in progress with Joao Caetano and Ethan Wan. It's going to be very brief about the double scaling limit and the central extension. So now I forget about the UN series, and now I'm back to rank 1 series. So the topic that I'm going to discuss now is the exponentially small corrections. So the large charge expansion of superconformal field theory receives exponentially small corrections, as is known from, especially in n equals 2 theory, you can just do the localization and confirm it. And there is a nice paper by Zohar and Alba and Luigi, which systematized the analysis in the language of matrix model. And so if you just compute it, then there are this kind of corrections. And the physical interpretation is that they basically come from massive BPS particles in flat space, because if you take large charge limit, then you can approximate things in terms of flat space physics. And this correction can be interpreted as a virtual particle propagation of massive BPS particle. And interestingly, you can consider if you have some marginal direction, you can consider some different limit in which these contributions gets enhanced and becomes order 1 rather than exponentially suppressed. And that's what people call a double scaling limit, initially discussed in this paper, I think, which is to take J equal infinity and keeping this fixed. So, and let me just remind you, what are these massive BPS states? So of course, I guess many of you know, massive BPS states in flat space are basically short multiplet of centrally extended Poincare supersymmetry. So this is like n equals to Poincare SUSY. And so we have like some extra central extension in this anti-commutator of Qs. And the particles or a representation which satisfies the BPS bound where m equals 0, m equals z, is a short multiplet, and it's the one that's responsible for the exponentially small correction. And this use of flat space SUSY is justified in the usual large charge expansion because in that limit, massive BPS, the Compton wavelengths of the massive BPS particle is given by this expression. And if you just take J to the large, keeping all GMLs fixed, then this becomes very, very small, and in particular, much smaller than size of ST-1. So you can just use the flat space SUSY. However, it is not justified in the double scaling limit because this mass of the BPS particle in the double scaling limit is just given by some order 1 number. So like a BPS particle actually sees the fact that they are living on ST-1 rather than on a flat space. So in that limit, this basically suggests that it's probably not appropriate to use this to characterize those states. And then you could ask, what is the symmetry governing this limit? And here is the answer. And the answer, especially for the n equals 4 10 mils, is actually what's called centrally extended SU2/2 squared symmetry, which was actually originally discussed by Bizert in the context of integrability in n equals 4 10 mils in the planar limit. So this is basically the algebra.
But I didn't understand the previous slide. Maybe I'm being dumb. I just didn't understand what the point. Maybe you can explain it again.
Okay, so this point.
What is you're saying that you're not allowed?
Well, I'm not saying that I'm not allowed, but there should be like a better description of those states, because
what do you want to do? Do you want to study their effect in flat space, or do you want to study their effect on the sphere?
Effects on sphere, yeah.
Ah, okay. So you
because double scaling limit sees the effect of the sphere.
Okay, so you want to try to understand their contributions to, let's say, 3-point functions.
Right. Yes.
You quantize them on the sphere. Okay.
Right.
You want to see how those symmetry generators act on the world line instant on.
Yeah, on the sphere.
Yeah.
Okay. Yeah.
Okay. So and so as I said, like the same symmetry was used by Bizert. So I'm going to give you like a very brief kind of derivation, sketch of the derivation, why this is true. But first, let me just say that the symmetry is used by Bizert and others to solve n equals 4 mils in the large n limit. But I should emphasize that in that limit is given by this limit, but now we are in a completely different limit, but the same symmetry plays an important role. Okay, so the sketch of the derivation. So it's actually very simple. So in order to do that, we just need to remind ourselves of the SUSY transformation. And in particular, like a very basic of SUSY transformation, like a Q acting boson gives you fermion, and Q acting on fermion, in the case of n equals 4 mils, spits out this factor, g mils times phi times commutator term. So this basically suggests that if you take Q square and in particular, like take appropriate like a combination of Q and Q, then you get this term. And in particular, by choosing like indices correctly, you can get scalar field, which gets VEV because of the large charge operator. So, and because of this, if you consider, for example, SU2 theory, and if you take a boson living on this off-diagonal part, so sorry, I should put minus sign here, off-diagonal part, then action of anti-commutator on such off-diagonal boson is given by g mils times v, where v is the expectation value that you get, that the field gets because of the large charge operator. And in addition, on RT times S3, because I'm really considering sphere, Q dagger, so the Hermitian conjugate of Q is given by S. So this consistency and this, because of that, consistency requires that the anti-commutator of S should also give you like basically the conjugate of this guy. And if you complete this algebra, then you basically get the centrally extended SU2/2 that I showed here. So what is it? And now the question is it useful? So it's useful for some purposes. So basically, for example, if you want to analyze the massive excitations around the large charge vacuum in this double scaling limit, they basically can be organized using the representation of the centrally extended SU2/2 square, in particular the short BPS representation. And that allows you to like classify the excitations, and you can actually like check that this is correct by doing some perturbative analysis. And it also helps us to determine the dependence of this like a large charge to Foucault coupling, GML square times J at all order. For example, one of the excitations, if you take one of the excitation and then like read off the energy of that excitation, then it's given by this expression, which you can just like check using the perturbation theory. But the symmetry analysis tells you that like it should organize like a resum into this expression, and you can actually confirm it up to this order, for instance, where G square is given by this lambda J. And this, by the way, so for people who know integrability story, this is a special case of like a Magnon dispersion relation, which shows up in the n equals 4 super-mils in the large n limit.
This wasn't known, I guess, from localization, right?
This wasn't known. Right, because I'm talking about massive excitation, and in general, you can like combine those massive excitation and create a non-BPS state.
Yeah.
Okay, so right, and in particular, and furthermore, like one of a J correction, which is given by interaction of those massive modes, are expected to be described by SU2/2 invariant S matrix, but this part is still in progress. Okay, so let me just make several comments. So the large charge expansion. So the nice thing about this is large charge expansion that relates the centrally extended Poincare SUZ, which classify particles in flat space, and the centrally extended SU2/2 square, which like classify the operator. So in some sense, like SU2 centrally extended SU2/2 is the S3 version of like a centrally extended Poincare SUZ. And as I said, like there is some connection to integrability approach. And in some sense, it's a bit similar in spirit to what was done in this paper, which discussed the relation between BPS particle index and superconformal index, because I'm basically saying that this algebra, if you take a decompactification limit, becomes this centrally extended Poincare SUZ because of Inanu-Wigner contraction. And again, there should be some similar story for n equals 2 super CFT, but in that case, like we only have a single SU2/2.
That's not enough to determine the mass?
That's enough. If the symmetry gets centrally extended, that's enough. Okay, so if there are no other questions. Mm-hmm.
Yeah, sorry, perhaps a stupid one. So, but couldn't you determine this? I mean, the double scaling limit, you can still do somehow perturbation theory, right?
Yes. So, yeah, that's a good. Thanks for pointing out. So this result based on this algebra is less impressive than what people did for large n equals 4 super-mils, because in the large n equals 4 super-mil, there are basically no other ways to study the spectrum. But in the double scaling limit of the SU to n equals 4 super-mils, we can basically use the semi-classics. Like,
yeah.
So in principle, like you can also get the same result from the semi-classics. It's
but
just like a.
Does this tell you anything about the G-square correction? Is that to the?
Well, I think like in principle, you can also get this from the semi-classics.
No, I'm saying you can. Does this tell you anything about 1/J or G-square?
Yeah, right. Well, I guess like if you work hard, you can also get get it from semi-classics.
No, but I'm saying this symmetry argument, does this inform you about higher order correction in the coupling, not the two?
Oh, higher order, like the symmetry argument becomes less powerful. yeah, 1 over j, we can say something, but at higher order, it becomes less powerful.
Okay, yeah, sorry, I didn't start.
Okay. So let me just go to the last topic very quickly. So now I changed the gear completely, and now I'm going to use some insights from large charge expansion and use it to resolve some confusions in holography. But actually, those insights are probably kind of like a very obvious things for people working on large charge expansion. So let me just give you the setup. So the setup is I'm going to consider the 3-point function in n equals 4 submills in the large n limit. And in particular, I take the 3-point function of BPS operators, but I take like 2 of them to be very large. And in particular, 2 of them to be like this particular Schur polynomial operator. And the last one, and this O, to be single trace operator. And as I said, and furthermore, I take this J to be the order n, where K or L, so this is not K times L, this is K or L, to be order 1. The holographic description of this correlation function is given by this semi-classical D-brane and quantum fluctuation emitted by this single trace operator. So basically, in order to compute this 3-point function, you just need to know how the dBi action of the D-brane gets perturbed because of this supergravity mode emitted by this single trace operator. And this problem was indeed studied back in 2011. And they wrote down the formula which expresses this 3-point function in terms of the fluctuation of deformation of the dBi and basis amino action. And this deformation is sourced by this like a bulk to boundary propagator coming from this local operator. And there is a similar fluctuation also for the sphere part. And the good thing about this 3-point function is that this is protected, so we can directly compare the weak coupling result and the strong coupling result. However, back then, people did the comparison, and the result didn't match, and there was no definite conclusion after that.
I'm sorry.
And it turns...
Is this what's called an extremal correlator?
This is not extremal. I'm actually choosing L and K to be different. And the reason why this is allowed is because n equals 4 system has SU for our symmetry, and I am choosing the like a rotation angle of these 3 operators to be different. So they are not rotating on a single U1 axis. And so the problem is not about extremal or non-extremal. It's actually a more serious problem. So, and it turns out they are basically missing 2 effects, which we called orbit average and wave function contributions. And to understand this, it's kind of like just easy to go back to this toy model, which is also discussed in this paper. So let's consider quantum mechanics living on S1. So theta runs from 0 to 2 pi. And we further assume that there is U1 symmetry, which shifts theta by constant. And then we want to compute this similar correlation function in the WKB limit, where J is large, H bar is 0, where H bar times J is fixed. And if you want to analyze it using the using in this limit, and because it's WKB limit, it's going to be given by some saddle point approximation. And so you first write this path integral, and then path integral, you assume that the path integral is dominated by some saddle point. And that gives you this expression. However, this expression by itself should be incorrect, and because of the simple reason. And because of the U1 symmetry, which shifts theta to theta plus C, we can, if you have one solution, theta 0, we can basically construct a family of saddle point solution, which is obtained by adding C to this theta 0 star. And because of that, the correct formula, we need to basically average over this number C. And that gives you this expression. And if you massage this expression a little bit, then you get this nice simple expression where you have some integral over C, and there is some contribution coming from the mismatch of the wave function factor from the heavy modes. So basically, we can do the same okay, first of all, I should say that the reason why previously people did a mistake is because they just took expression like this. And so the correct formula is that you can basically repeat the analysis using the D-brane word volume action. And that is going, and in this case, because there are two, like a U1 direction, which is one is given by conformal and the other is given by U1 charge, you have like a two direction to integrate over. And the wave function is given by a similar plane wave expression. And just repeating the analysis for the simple quantum mechanical formula, we arrive at the expression, which is given by this formula. So now you have two integral. One is due to U1 charge, and the other is due to conformal charge. And this one is similar to what previously people analyzed. And then on top of that, there are like wave function contributions. And if you just like take this expression and integrate, you get this complicated looking hypergeometric function. Although it's complicated, nicely the result matches with field theory. And the field theory computation is also a bit complicated because you need to deal with combinatorics, but you can basically reproduce this to F1.
Shota,
yes.
Would it be correct to say that it's like they were looking at fixed chemical potential instead of fixed charge?
Oh, I see. That's.
I'm just saying. I mean, the expression that you wrote there, I might read like this. You know?
You mean this one?
No, the last integral that you've written also. I mean, that's.
Oh, this one.
Yeah. I mean, if the deltas and the j's are large, that's essentially a Legendre transform.
Ah, okay. So I guess. So in that case, I probably like for fixed tau 0 and phi 0.
Right.
You are saying that it might correspond to like chemical potential. Yeah, that's a good point. Yeah,
that's what I'm saying. It looks like.
Yeah, that's a good point indeed. Yeah. Yeah. It's true that if you write, like you can also like absorb this everything into the kind of like a DBI word volume action. And if you try to do that, what you are gonna do is basically do the Legendre transformation.
Right.
So yeah, I agree. It's probably true. Okay. Yeah, I agree. I think that's a good interpretation. Okay, so let me just make some other comments. So the computation can be generalized to ADS 4 times S7 over ZK or ADS 4 times CP3. Those are two things we did, possibly more. And this is actually a bit interesting for, in particular, ABGM theory, or like ADS 4 times CP3, which is due to ABGM theory in the planar limit, because the 3-point function is not protected. So this computation gives you some solid prediction about the strong coupling behavior of the 3-point function of BPS operators. But in order to really like check that it is correct, we need to develop some integrability approach to test it. So, okay, conclusion. So today I discussed 3 topics. So the first topic is about large charge BPS operators for higher rank superconformal field theory. And in particular, I pointed out the importance of the degeneracy of BPS operators and the relation to the Higgsing patterns. And furthermore, I discussed that in the large N limit, if you consider this operator, that's going to be due to spherical D-brane. And that gives you some kind of holographic version of the large charge EFT. And the second topic I discussed is the double scaling limit, which is governed by centrally extended SU2/2 symmetry. And finally, I discussed the holographic correlation function of D-branes, and I pointed out that the orbit average and the wave functions are important. And of course, like an interesting question in this direction is what happens if operators are heavier, in particular, if the operator corresponds to geometry. Is there anything like orbit average or wave function contribution that we need to include? And that's certainly interesting to discuss. And let me end with my personal wish list about large charge expansion. I'm personally like interested if large charge expansion can say something about quantization of membrane. And So the idea is to consider a large charge operator in ABGM theory in the large n, but k equals 1. So it's not in the 't Hooft limit, but it's going to be the limit in which the dual is given by membrane, M theory. And similarly as like a D-brane that I discussed today, there are two interesting holographic duals. One is the M2 brane, rotating M2 brane, whose volume is given by RT times S2. So this is the analog, direct analog of this D3 brane that I discussed today. And there is also M5 brane as well. So in the M2 brane, the size of the M2 brane is controlled by the charge. And it'll be very nice if we can use the large charge EFT or bootstrap or localization to study some quantum fluctuation on a membrane and can say something about quantization of a membrane. And in particular, this might be interesting because if you take a large charge limit, there might be some connection to what's called BMN matrix theory, which is a deformation of the BFSS matrix model, and which is supposed to describe an M theory on PP-wave background. And the PP-wave background is basically like you can get it from ADS spacetime, ADS 4 times S7 spacetime by looking at the geodesics of like a highly fastly rotating particle on S7. So this was it, and this is the end of my talk.